Hi, my name is Joseph Panipi and I work in the water utility industry in Western Australia. The reason for this video today is to run you through an app that a few colleagues of mine and myself developed, which is aimed to help people who work on metallic services get a better understanding of the electrical risks associated with the job, the kind of PPE they need to wear, and how to do the job safely. This, however, is not a replacement for educational qualifications or the correct competency training that one needs to first attain in order to be eligible for the job. It is purely intended for educational purposes, and we hope it gives you a better understanding to be able to visualize the different scenarios that could give rise to an electrical hazard when on the job. So without further ado, let's get right into it. What we developed is a graphical interface, which is a simplified representation of a typical residential household's electrical distribution. You've got a transformer outside the property boundary, which feeds power through electrical cables, an active and a neutral cable in the instance of a single-phase supply, or it could be three individual wires that are braided together to appear as a single wire, and a neutral return wire. We'll talk a bit more about the neutral wire later on during the presentation. Downstream of the supply authority meter box, you would have a distribution box, and generally these are located inside the house, from which you operate a main switch that then energizes all the loads connected to power sockets within your property. The key message to note here is that electricity originates at the source. This source could be a diesel generator, or it could be this transformer that's illustrated in this instance, or it could even be a power station that feeds this transformer. The key message to note is that electricity originates at the source and travels via the active conductor into the property, enters an appliance or a load, and then does work and returns back through a neutral wire, hence the term return wire. If there was a fault in the neutral return path in the property, for example, one realistic scenario could be that the terminations on the neutral wiring at the meter box could become loose, or there could be a build-up of dust or dirt, in which case that would create a high resistance path for the electrons in the loop to continue flowing back to the transformer. If such a fault were to occur, then electricity that originates at the transformer will try to find its way back to the exact same transformer through an alternative path. In this instance, the electrons flow through the neutral bar down into the earth bar and any metallic surfaces that are connected to the earth reference or earth bar of the property, and eventually find their way back to an earth cable that is installed remotely at the location of the transformer. I'd like to draw your attention to the number of amps that are measured on the active wire. When the wiring in the property is good, the amount of current measured on the active wire will be the same as that measured on the neutral wire. Whereas in a fault scenario, because there are fewer electrons returning back to the transformer via the neutral conductor, the current measured across that is correspondingly low. Under these circumstances, if we sent a worker to go and replace this water meter, then they would be exposed to a touch voltage. What's interesting to note is that the only time you would notice a touch voltage in a fault condition is if there were loads turned on in the property. If an operator was to be sent out to field to replace this water meter without any prior knowledge of a pre-existing fault within the electrical wiring of this household, then he or she could start the job with a touch voltage of 0 volts, and out of the blue, the fridge kicks in. Either that or the kids come home from school and crank up the aircon and suddenly want to watch TV. Then there's an unexpected rise in touch potential from 0 to 30 volts, which could be even more dangerous if there was resistance on the pipe, which would increase the touch potential to anything above 50 volts, which could potentially be lethal. It is for this reason that operators are required to install an instrument called a Plum guard, which requires to be clamped on either sides of the water meter or the section of pipe they intend to work on, and also drive an earth reference stake into the ground. The Plum guard does not have a visual display as that indicated on the simulation, but is designed to raise an audible and a visual alarm if it detects a voltage greater than 6 volts between either sides of the metallic surface that's being worked on across to the remote reference earth that's installed on site. While the Plum guard serves merely as an administrative control to warn the operator of any potential voltages, a bridging cable must be installed to bypass the flow of current across the section of pipe that's being worked on. With bridging cables installed correctly, under a fault condition, electricity will now flow via the bridging cables instead of through the water meter or the section of pipe that an operator may be working on. That section of the pipe can either be cut or a water meter can be removed and replaced with a new one and reinstalled without presenting an electrical hazard to the operator on the job. Bridging cables are effective if and only if the water pipe is a good metallic conductor of electricity. That is, if bridging cables were not installed and the water meter was removed, then the touch potential increases significantly to about 80 volts. Beyond that, if the neutral connection within the household had completely failed, that is, the connection had completely come undone, or what's called an open circuit neutral, then the touch voltage rises to a dangerously high volts. If the service pipe that feeds the property is a non-conductive PVC pipe, then it does not form a good return path for electrical current back to the transformer, in which case a poor neutral connection will always present a touch potential at the property. If the neutral continues to deteriorate, or in some cases becomes completely open, then the touch voltage increases to a dangerously high voltage. Under these circumstances, even a properly installed bridging cable is not effective. It is for this reason that operators must at all times wear electrically rated insulating gloves. In some ways, this simulation demonstrates that bridging cables alone are not an effective means to mitigate electrical shock in the event the service pipe is a non-conductive PVC pipe. Although the Plum guard will notify the operator through an audible and visual alarm if it measures anything above 6 volts, wearing the correct electrically rated insulating gloves is the best way to mitigate an electrical shock. Generally, under these circumstances, those living within the household would also experience electrical shocks, and one would hope that those would be reported to the relevant supply authority for further investigation. People living within the household would also notice a dip in voltage and a failure in their electrical appliances, as the voltage within the house would be far less than what is needed to run most appliances. We hope that running this simulation has given you a better idea of the various scenarios that could give rise to an electrical shock risk when working on service pipes. Merely using bridging cables by themselves may not be an effective means to mitigate the risk of electrical shock. Furthermore, we also hope that it's developed a sense of appreciation for why organisations tend to have very strict and mandatory work procedures and PPE requirements when working on service pipes. If this is something that you do not do on a daily basis, we hope that watching this tutorial has given you a bit more of an understanding on how to recognize early signs of electrical faults within a residential household and perhaps escalate that to the correct supply authorities for action to be taken. My name is Joseph Benepi, and thank you for watching this tutorial.